did I know that while I was lecturing to you on Friday, my wife snuck into my office and decorated it? That's love. That's what love is, right there. So, had a pretty good birthday. It was pretty solid. I went home and I drank a bunch of beer and played some video games, and then we went out for dinner and came back and watched a really scary movie. I love scary movies, so. Yeah.
What movies you watch?
We watched a movie called Absentia.
No. What's it about?
It is. Let's just talk about movies. Absentia is a movie about. So this guy disappears, and his wife ultimately. It's been 7 years, and so she decides to file for his death in absentia. Right? He just disappears, and so she's like, "All right, he's dead," and so we can legally just call him dead. And then weird things start happening. Yeah.
Weird things.
I don't want to spoil it, but yeah. So I won't say anything else. In case you watch Absentia. Okay, alright, so I have exams in the box. You guys can again just stare at those for 40 minutes or so. We'll talk about it at the end. I'm really frustrated by technology today, so I'm going to have to use PowerPoint. Yay! I hate PowerPoint. So anyway, that's the best I'm going to make work. So fortunately everyone, or at least I hope everyone, was able to download the worksheets that I handed out, because we're going to be annotating those as we go. Chatty. Okay. So just a quick review. Hopefully you've seen. So we've seen all the different pieces of information we're going to use in analyzing NMR spectra. And so just a brief rundown about how you're going to do this as we go, right? So first off, we'll talk about this in a minute, but we'll talk about the index of hydrogen deficiency. And so there's this really neat little formula that we can plug our stuff into and to help us determine how many rings or pi bonds there might be. So we plug all our atoms in, and so say we get the number 2, and that tells us there's going to be at least 2 rings or pi bonds. That's computed just by how many hydrogens are there. So that'll be good. And so then what we'll do is we'll determine how many different sets of signals, and so we know we have different signals that we're talking about protons that are not equivalent, and so that tells us how many different sets of protons we have. We'll determine the integration, and so the integration tells us how many protons basically belong to each signal, so it helps us know how many we're looking for. We'll talk about chemical shift data. We've already talked about that. We talked about, let's see, electronegativity having a role, as well as the anisotropic effect, right? So the pi bonds do weird funky things with the way they align themselves, which changes the shifting as well. We talked about splitting, and so splitting gives us really good information about what kind of protons we have on neighboring carbons. So again, really important pieces of info. And so what we'll do is we'll take that information and we'll put together fragments. We can't always just directly draw the molecule, but once we have our fragments, we should be able to put a complete molecule together. And so at the end, it's always anything you do in life, it's always going to be important to just kind of do the does it make sense test, right? So you look at your molecule, think about how many signals you would expect, and make sure that the spectrum that you've been using makes sense, right? Okay, and so this is really something, this is very much, our theme song today is Jigsaw Puzzle by the Stones, and so this is very, very puzzle-like, and so I'm going to have some practice problems for you to do. We're going to be doing 2 weeks worth of them in lab, and so this is really the way we're going to get it good at this is by diving in and really getting our hands dirty with it. So, all right. And like I said, if you're not in lab, this is probably a good one to come to. So email me. We'll squeeze you in somewhere. That way you can get the same practice, or at least I'll give you the problems. All right. PowerPoint. Let me make sure I can draw okay. Okay, I can draw okay. All right, so we're just going to go straight to our spreadsheet. So what you can see is you can be given something like this. So here's a spectrum, and in all cases, you're going to be given a molecular formula, and that's going to be really useful because we can plug that into our IHD formula to figure out how many rings or pi bonds there might be. So to start out, that's what I would do. I'd look at our molecular formula at the top. We've got C4H8O2. So if we just plug all these in, we've got 2 times our carbon. So we've got 4 carbons, no nitrogens, minus 8 hydrogens, no halogens, and plus 2. So that's 4 times 2 is 8, minus 8 is 0, plus 2 is 2. Divided by 2 equals 1. All right, so this means we have 1 ring or pi bond in our molecule. Let's see if I can choose a different pen here. Okay, so that gives us a little piece of structural information. So there's going to be lots and lots of little pieces of clues that kind of tell us what's going on. All right, so the next thing we might look at is the different number of signals we got. How many signals are we seeing? Yeah, we're seeing 3 signals, right? So those are labeled with A, B, and C. So in this case, and so certainly on any homeworks that I'll give you and on an exam, this might show up a little better. But what we're looking at is a quartet there. So when you see a quartet, how many signals is that actually counting for? 4, 5, how many protons does it represent? It's just one signal, right? It's just being split into a quartet by neighboring protons. So that's why, even though we've got 4 peaks there for signal A, we've still just got, we count it as one signal. Okay, so what we're going to do is, like I said, you can see this little red line, and so the length of that red line indicates to us what our integration is. And so we could say, so you'll have numbers specifically when we do it, but what we can say is that this thing is about 2/3 the height of that, and so what we're doing is we'll say this peak A has an integration of 2, and so peak B is going to integrate to about 3, and peak C will integrate to about 3. Does that make sense given our molecular formula? Yeah.
Are you looking at the little red squiggle? Or
Yep.
the height?
Yep, we're looking at the red squiggle. So basically from the difference between here and here compared to the difference between here and here. So you can see that the distance for signal A is about 2/3 the height as signals B and C. So we can
So
go 2, 3.
the squiggles are the signals and the black ones are the peaks?
Yeah, the black peaks are basically that's our information. So these red lines, this is just where the computer has integrated the area under those peaks. So that's what the red line represents. Okay, so furthermore, so we've got our integrations. We want to think about shifting. Now, between peaks A, B, and C, which are the most de-shielded peaks? It's definitely A, right? We know that because it's downfill, right? So we've got a peak that's been shifted downfill. And so when we looked at that last time, we would assume that that's going to be next to something like an oxygen, a nitrogen, or a halogen, right? So we can assume that it's near something that is pulling electron density away and de-shielding it. So is it next, what do you think is next to, oxygen, nitrogen, or halogen? Well, there's nothing but oxygens, right? So we certainly are looking to most likely a CH2, right? Because it integrates to 2. So we're most likely looking at a CH2. Now let's finally talk about the coupling. So I've already said that the splitting here is what? It's a quartet, right? So we're looking at a quartet. And so if it's a quartet, that's going to be highly indicative of a CH2 group that's probably next to what? Would a CH3 turn it into a quartet? How do we determine how many peaks we'll have given neighboring hydrogens? Remember the N+1 rule? And so if we had a neighboring CH3, we'd have 3 hydrogens. And so if we plug that in, we would expect 4 peaks. And so is that how many peaks we have here? Yeah. Yeah, so that makes perfect sense. So because we've got a quartet, most likely what we're talking about is a CH2 next to a CH3. And so let's see. Let's think about what fragment we could have then. So we'll go down here and say that we've got most likely a CH3 next to a CH2. And so furthermore, we can also draw in a little piece of information based on this shifting. So we said that it's most likely going to be next to an oxygen, a nitrogen, or a halogen, right? Because it's so far downfill. And so furthermore, what we can assume is we're going to have some fragment that looks like that, right? That's all we can know from the information we've seen is that we've got that little piece of a fragment. So that's going to be pretty useful. All right, so this here, which I could easily change color. This here is going to be A. All right, so in this fragment alone, we've also got a CH3 here, right? So we would expect somewhere to be a signal that integrates to 3. CH2 is just basically off of this integration, right? We know this peak is accounting for 2 total hydrogens, and so that's indicative of a CH2. Yeah. Okay, so we also expect there to be a signal that corresponds to this methyl group. Now, do we have a signal that has an integration of 3 protons? Sure, we have B and C here, right? And so furthermore, what kind of splitting would we expect here? We would expect a triplet, right? Because we've got a signal, a proton signal here that is next to 2 hydrogens. So N+1, we would expect a triplet. Do we have a signal that integrates to 3 and is a triplet?
C.
Yes, certainly. We look over here at peak C, and that's going to fit the bill. So what we've got here is most likely a CH3 next to a CH2. And so what that tells us is that most likely this is going to be signal C right here. Okay, so finally we've got, and let's also make sure we know that this is split into a triplet. All right, so finally we've got signal B. And so signal B is, it's a little more downfield than we expected, but what's the splitting on signal B?
Singlet.
Yeah, it's very much a singlet. So is it going to have any neighboring protons? It's not going to have any, right? Because N+1, so N would be 0 if we're seeing a singlet. So it's got no neighboring protons. But the chemical shift, we'll just call it a slightly de-shielded alkane. So we know it's slightly de-shielded because alkanes typically come in around 1, but this thing's a 2. So there must be something that's withdrawing a little bit of electron density, but not much. So what we'll do is we'll just say that, well, we've got a CH3, right? We don't really know what it's connected to. Okay, so let's think about what we've got. We have used up, in our fragments, we've used 3 carbons, so we've used C3, and we used 3, 6, 8 hydrogens, and we used 1 oxygen. So what's left over? What atoms have we not used? Yeah, so we have left over 1 carbon, 1 oxygen, and furthermore, have we used our hydrogen deficiency unit up, right? We ended up with a 1 here. Do we have a ring or a pi bond in our fragment yet? No, we don't. And so is there any structure we can think of that would have a carbon, an oxygen, and a pi bond? Yeah, think about the product of an ozonolysis reaction, right? We end up with a carbonyl. And so what we could assume is that our last fragment is going to look something like this. All right, so is there any way we can put all these together now that we've got 3 fragments that have used all the atoms? Sure, so we've got a terminal piece here, a terminal piece here, and then a piece that we can pretty much plug in between the 2. And so let's see what happens if we fill that in. We're going to have CH3 next to carbonyl and so we end up with a structure that looks like that. All right, so does that make sense? How many proton signals would we expect to see for this molecule? We would expect to see 3. Is that what we've got?
Yes.
Yeah, it sure is. And so we've also talked about that. We've seen that the splitting makes sense. And furthermore, the chemical shift is makes sense. So what you can notice here, a piece of info that'll be useful going forward, is this CH3, it wasn't directly next to an oxygen, right? So it's not shifted down to 4, but what it is directly next to a carbonyl. And so the carbonyl is a little bit electron withdrawing, and we end up seeing that shifting from 1 to about 2 right there. So just a FYI on that. Typically, something next to a carbonyl is going to be around 2 or so. Okay, if this seems intimidating, trust me, we're going to get lots of practice in lab and such. That's why we have the labs, so we can basically get some one-on-one in that case. Okay, so let's do another one. Oh boy. Okay, so let's go ahead and do our our hydrogen deficiency. So in this case, we've got 2 times 8 plus 0 minus 10 minus 0 plus 2. So that's 16 minus 10 is 6 plus 2 is 8 divided by 2. So we're going to have 4 pi bonds or rings. So that can be a combination. That doesn't have to be 4 pi bonds or 4 rings. That could be 1 pi bond with 3 rings or 3 pi bonds with 1 ring. It's just going to be the number of pi bonds and rings adds up to 4 in this case. All right, so how many different signals do we see?
5.
Yeah, we see 5. So let's go ahead and say we've got A, B, C, D, and E, just like that. And so furthermore, our integrations, and again, these don't show up as well as I would like. So our integrations, we have 2, 3. And so over here, we've got 2, 2, and 1. And again, that's basically, it's just from the height of our red line that's integrating our peaks there. So I'm going to have to just give that to you. So let's start at A and work our way down. Who remembers where we typically, or at least what kind of fragment would give a chemical shift down around 7 or 8? All right, so an alkene was more like 4.5 to 6.5.
It was that weird example.
But we saw that what the anisotropic effect gave a certain type of molecule like really far downshift.
Is that triple bond the one that C?
It wasn't a triple bond. Triple bond's around 3, so it's a benzene type molecule, right? Whenever we have benzenes, we see a chemical shift of 7 to 8. So anytime ever that you see something down here around 7 to 8, what that's indicating is that we've got benzene protons. All right, so benzene itself has how many protons? It's C6H6, right? So it's got 6 protons. So we have 6 protons here. Now we have 5 protons. So what that's indicating is that we have a benzene, but it's not just benzene. It's connected to something, right? Such that one of those protons has been replaced with connectivity to the rest of our molecule. All right, so we've got 2 and 3 here. And so for both cases, our chemical shift indicates a benzene type structure. And so furthermore, we've got this this hydrogen deficiency of 4. And so how many rings are in benzene?
3.
Well, how many pi bonds are in benzene?
3.
That's 3, but then how many rings? There's 1. Do we have 4 units of deficiency that could basically explain why we have benzene in this case? Sure, right? So a benzene, remember, looks like this. And so to have a benzene-like structure, it automatically requires an IHD or 4 because we've got 1 ring and 3 pi bonds, and so that's exactly what we've got in this case. Yeah.
Okay, so probably is a dumb question. So a ring is when the structure is closes on itself and is cyclic.
Mm-hmm.
Okay.
Yep. Just a cyclic structure, and every time you've got a cycle that you complete, you've got 1 ring. All right, so we've got 1 ring here. So we've got a benzene-like structure. And so in this case, if we were to blow this up and look at the coupling, what we would find is that it's not nice and pretty. And so what we end up calling that is a multiplet. So what multiplet means is there's splitting in there, but we can't look at that and easily decide if it's a doublet or a triplet. We just know that there's some splitting going on, so we just say multiplet. All right, so what this is indicative of is going to be a structure that looks like this, right? So basically, we've got a benzene-like molecule that's stuck on the end of some other fragment over here. So does that explain why our integration is 5 instead of 6? Yeah, definitely. We've got 1, 2, 3, 4, 5 protons on here, but that 6th proton that we would expect there, it's not there. It's been replaced basically with the rest of the molecule. And so we see the integration is only going to be 5 for our benzene case. Okay, so let's keep working our way down. So the integration on peak C is going to be 2. And so that chemical shift, we saw this in the last structure. What is that indicative of when we see a chemical shift down around 4? That is always going to be indicative. It is going to be right around an oxygen, nitrogen, or halogen. And so in this case, what does it have to be? Oxygen. It's got to be an oxygen, right? So basically, we've got protons that are being de-shielded by an electronegative atom next to it. So in this case, it has to be an oxygen. So furthermore, we've got a CH2, most likely, right? Now, the CH2, what's the splitting? It's a triplet. So we've seen something that looked like this already. And so what we've got is most likely a CH2 next to what? Probably a CH2, right? Because we know it's the N+1 rule. And so if we're split into 3 peaks, that tells us that there are likely 2 neighboring protons. So most likely what we've got is a CH2 next to a CH2. All right, so let's see if we can draw that fragment. We have CH2 next to CH2. And so furthermore, what has to be on the left side?
Oxygen.
An oxygen, right? And we know that because it's downfield. So we draw in our oxygen. And most likely what we've got is some fragment that looks like that. All right, so this is going to be C. And so if this is a CH2, and then this is a CH2, well, certainly we would expect this to not be a singlet, right? Because it's going to be split by these protons. So do we have a peak, another remaining peak that's not a singlet?
Yeah, D.
Yeah, all right, so we look at peak D, and so we can see that's split into a triplet. And does that make sense for this being D?
Yeah.
That also tells us that, are there any other protons over here?
One. No. No.
There aren't any, right? And so what we've got is a pretty solid fragment, so we can go ahead and assume that these protons are going to be peak D. So if we fill in our information, we see that the integration is 2. We see that it's a triplet. And so we can assume that it's the protons that we've drawn in right here. Okay, so we have 1 peak remaining, and the integration is 1. Now this peak is a little bit interesting because how would you explain its splitting?
It looks like a singlet.
It looks like a singlet, but it doesn't look as skinny as the typical singlet we've seen, does it? And so one thing we can say about this peak is that it's very, very, very broad, all right? And so that's going to be another piece of information that's a clue whenever we're interpreting these spectra. So anytime you've got a very broad singlet-looking peak, what that's indicative of is a proton, that it is either an OH proton or it is an NH2 proton. And so whenever you see broad, you should think, all right, that thing is probably connected to an oxygen or a nitrogen. Yeah?
Going back to the CH2 next to the CH2, how do you know it's next to a CH2 and not a CH3?
So we know it's not a CH3 here because if it were a CH3, the N+1 rule would tell us that we would expect a quartet. But we don't see a quartet, we just see a triplet. And so that tells us that we can't have a CH3 there, right? It must be a CH2.
So where's the N+1 rule?
So the N+1 rule just tells you, based on how many peaks you have, how many protons there are on neighboring carbons. So if we've got a singlet, N must be 0, because 0 plus 1 would give us 1 peak, right? If we have 2 neighboring protons, we'd have a triplet, 2 plus 1, 3 peaks. If we had 5 neighboring protons, it would be 5 plus 1, and so we'd expect a sextet. Yeah.
I'm a little confused as to why the oxygen is on the left side of the
So you could draw this fragment perfectly fine with the oxygen on this. It would be the same thing, right? You'd have the same exact fragment. Yeah.
Why are there 2 separate signals for the
Yeah, and so what we've got is, since we have a point of connectivity over here, really what we've got is we're going to have a pair of equal protons here, a pair of equal protons here, and then 1 proton here. So what we've really got is 3 different types of protons, but because they all shift very similarly, and they all end up with some sort of splitting pattern, what we get is overlapping peaks. And so all these things are going to smudge together. And so that's why we can't say, oh, this is a nice pretty doublet or a nice pretty triplet. It's because they're smudged together, and so we just look at it and say, well, clearly there's splitting going on. We'll just call it a multiple.
So would that be always look like that was kind of 2 signals?
That is fairly common for benzene, but certainly there can be cases where it's not just 2. You could end up seeing 3 different peaks. Yeah. Good questions. Okay, so let's see. We know that we've got peak E, and so do you think it's an OH or an NH2? Yeah, I'm guessing it's probably an OH. And so what we can assume is what we've got, since we've only got 1 oxygen, is an OH right there, right? Because that oxygen's got to be connected to something. And so we only had 1 more atom to play with, and it was that hydrogen. Yeah?
So wouldn't that change the neighboring hydrogens for the CH2?
That's a good point. And so another thing that we should talk about when we talk about OH2s and NH2s, these protons here are very rarely split. And And so what happens is these are almost always going to show up as a singlet, and furthermore, they're going to do a very, very bad job at splitting this. And so where you might say, okay, this CH2 is next to 2 protons here, and then it's also next to this proton here, right? We would expect N to be 3, so N plus 1 to give a quartet. But because it's an OH proton, and it's just very bad at splitting, it actually doesn't show up in the spectrum. Yeah. And so that's why we only ever really see a singlet here, because at the same time, we would look at this proton and we say, all right, what's next to CH2, right? And so what would we expect for the splitting here?
Triplet.
You'd expect a triplet, but we don't see that. We just see a singlet. Yeah. Okay. So in this case, have we used all of our atoms?
Yes.
Yeah, we have. So can we put that together?
Yep.
I think we can. So we would end up with a molecule that looks like that right there. How many different protons do we have in this molecule? Let's just count left to right. All right, so clearly this is its own thing. This is a signal. This is a signal. And then over here, we've got 4, 5, and 6. And so while we only have 5, the reason is really there's 3 signals in here, but the benzene just gets smushed together, and so we only see 2 show up. Okay. And in fact, in these cases, it might be a little easier to think, all right, just ignoring benzene, how many signals would we expect? We've got 1, 2, 3, and that's exactly what we see in the non-benzene region. So, all right. What do you guys think of this?
It's going to take some time to get used to.
It takes some time to get used to, but it really is, I mean, it very much is a puzzle-solving process. Another example. All right, let's see. I'm a little out of order. Okay. So it's already filled in for you. If you do the math, you'll see we've got 5 rings or pi bonds, so that's a lot of hydrogen deficiency in this case, so we're going to have some stuff going on. Now, we look down here, we see we've got 2 peaks in the region of 7 to 8, right? And so furthermore, our integrations are 2, 2, and over here on the right, it's actually, let's say, 1, 1, and 3. All right, so that's our integrations. Does that make sense given our molecular formula? How many protons do we have in our molecule? 10. Is 10 a multiple of 3 plus 1 plus 1?
Yes.
And so what does that tell us this 1 actually is? It's actually a 2. So really what we've got is a 2 there, a 2 there, and then what over here? A 6. All right, so we've got 2, 2, and 6. Does that add up to our molecular formula?
Yep.
It does, so now we're good. All right, so again, anytime we see molecules in this region of 7 to 8, what does that indicate? It indicates benzene. All right, so we've got A, B, and C, and so our integrations are 2 and 2. So the chemical shift indicates a benzene-like structure. If we look really close in here, what we're actually able to find is that in this case, we see that our benzene signals are spread out a lot more. And furthermore, we could look at this, and we could actually pick out some splitting. It's not just a multiplet. What do you see in both of these peaks? Yeah, what we've got are doublets. So we've got a doublet for peak A, and we've got a doublet for peak B. Furthermore, how many total benzene protons do we have? We have 4 total benzene protons, telling us that how many protons have been basically ripped off of our benzene in this case? 2, right? So if we rip 2 protons off and we have some form of substitution, there's 3 possibilities, right? So we could have the fragments coming off of basically adjacent carbons, which we call ortho. They could be meta, which is basically they have 1 carbon between them, or they could be on total opposite sides. Now, looking at the possibilities here, ortho, meta, and para, which ones basically have 2 equivalent protons?
Para.
Yeah, so para, what about meta?
It's the distance, they're not the same.
Yeah, so meta doesn't, right? Because we've got 1 here, 2 here, and 1 here. What about ortho? How many signals, proton signals, would we expect on that benzene? Also tubes. So we could have ortho and we could have para. But what we can do is we can use our splitting information to give us more info. So if we had a proton here, following the n+1 rule, what would the splitting be expected to be? We'd have a proton here and a proton here, right? So we'd have 2 plus 1. We'd expect a triplet. Do we see a triplet for our benzene protons? No. So what we've got are a couple of doublets. Would this make sense for a couple of doublets?
Yes.
This proton's next to how many protons?
The 1.
1. What about this one?
1.
What about this one?
1.
What about this one?
1.
And so all of the protons in this pair substitution are next to one other proton, and so we would expect doublets for every peak. So what that indicates is that we've got a benzene-like structure that is most definitely in the para conformation, or not para conformation, para structure. Yeah.
So because the A and the B are identical, like they literally.
Well, they're not identical because they have different shifts.
Well, not
right?
because of the shifts, but like the structure of the signals are identical.
Right, they're both
Would
doublets.
that constitute it being para without having to really go through
That-
that process?
Yeah, I think, let's see if we can make that a rule. Anytime we see a couple of benzene peaks where both are doublets, I think we can only have para substitution in that case. Because if we had ortho substitution, we would expect a doublet for this one, but a triplet for this one. So that would be another piece of another clue that we could use for info. All right, so let's see. One fragment we most certainly have is going to be a para-substituted benzene. It looks like that. All right, so then let's look over here. Signal C. All right, so how many protons are there? There's 6 totals. Now, what does this look like? What's the splitting? It looks like it could be a double. Let's write that down and think about it for a second. All right, so it looks like it could be a doublet. It corresponds to 6 total protons. And then furthermore, by the chemical shift around 4, what does it indicate? It indicates that it's next to an oxygen, right? Because we're seeing it downfield quite a bit. So, likely, we are next to an oxygen in both cases, or at least in this one case. So, if in fact we have a doublet, let's think about what that indicates. So if it's a doublet, and we've got 6 protons, what other kind of peak would we expect somewhere in our spectrum? These must be split by 1H. And so somewhere in our proton, or in our spectrum, what we would expect is one hydrogen being split by how many? By 6, right? We'd have the other possibility, right? So if these signals right here being split by one proton into a doublet, that proton that's doing the splitting would have to be somewhere being split into 7 peaks by all 6 of these. Do we have another peak anywhere?
Well, not that we can see.
Not that we can see. And so I'm going to here's a hint. There's nothing else to the right. This is the entire spectrum. And so does that indicate that this is in fact a doublet?
Is that a 6 doublet?
Yeah, and so what it is instead of a doublet, what we've got is 2 singlets. And it has to be 2 singlets because there's no other protons in this spectrum that could be doing any splitting, right? Yeah, Gabby?
Can you explain why the doublet doesn't work?
So if we got a doublet, let's think about what this structure could look like. So if we've got 6 being split by a doublet, that would indicate something that looks like this. So we have to have some symmetry. All right, so what we'd be looking at, this would be our 6 equivalent protons. And so it would be split by this proton right here, right? It would split all of these into a doublet. Now, we'd also have to have this proton showing up somewhere, right? Furthermore, how would this be split? This would have to be split into a septet. Do we have anything anywhere being split into a septet?
No.
Do we have any signals anywhere else?
No.
We don't. And so what that tells us is this can't be a doublet because there's had to be something doing the splitting. And so instead what we've got are 2 singlets. And because both singlets are around 4, what does that indicate?
Oxygen.
They're both next to an oxygen of some kind. So what we've got is going to be an OCH3 and another OCH3. Now, are they identical? Do they have the same identical chemical shift?
Looks like it.
Well, they don't, right? Because we see 2 different peaks. If we see 2 different peaks, we're definitely seeing 2 different shifts. And so they're different a little bit. All right, let's think about what we've got left over. So we've got 1 carbon left over.
I have 1 oxygen.
We have 1 oxygen. What else do we have left over?
That should be it. What's in this count?
So our hydrogen deficiency, we had a number of 5. How much hydrogen deficiency have we actually used up in our structure?
4.
4. So we've also got 1 unit of hydrogen deficiency. Can you think of something that would have hydrogen deficiency with a C and an O? We already did it once. That is very, very indicative of a carbonyl, right? So we wouldn't expect any proton peaks, but we've got these 2 things, and so ultimately now we've used up 1. Our second comes from the ring, and then 3, 4, 5. So we've used up all 5 units of our hydrogen deficiency. All right, so let's think about what kind of structure we could have. We've got 2 terminal pieces, and then 2 pieces that could go in the middle. So let's go ahead and make this a terminal piece. So let's see, we've used this, and we've used 1 of these. And so the only other thing we could have would be our carbonyl here, and then a structure that looks like that. Okay, so how many peaks would we expect in this molecule? How many different sets of protons do we have here? Yeah, we've got 1 here and 1 here. So the 2 methyl groups, are these methyl groups equivalent? They're not, right? And so that's why we see different chemical shifts here. It can be a little misleading because they're so close together that we initially think it's a doublet, but in fact it's just a singlet. And so here we've got these 2 that are equivalent and these 2 that are equivalent. So we expect 4 different signals. Is that what we've got? Yeah, we've got 4 different signals. And so I can't think of anything that would go against basically what we just figured out. Okay. Let's see. What time is it? I don't know.
10:37.
10:37, 10:30. All right, we got a little more time. Okay, so let's talk about carbon spectroscopy for just a minute or 2. So we've talked about proton spectroscopy. Yeah.
So commenting, why is it just labeled C rather than having C?
Just because when we initially looked at it, we expected that to be 2 doublets. But in reality, what we found is this right here. We've actually got 2 different signals there. All right. So let's talk about carbon spectroscopy for a minute. So certainly I told you this proton NMR spectroscopy is the most commonly used, but you can also do carbon. Now, is carbon-12 NMR active? No, but carbon-13 is NMR active. And so what that means is since that naturally we find that about 1% of carbon in any given sample is carbon-13, what we can do is do spectroscopy on basically those carbons. Now, since there's not very many of them, the signal ends up being really, really, really weak. And so typically, a typical proton experiment you can do in 30 seconds or so. A typical carbon experiment might take you 10 to 15 minutes. So it just takes longer because the signal is so much more faint. But you can do it. Okay, so one thing about carbon-13 splitting is that it just doesn't happen. And so why is that, you think? Yeah, so is a carbon-13 nucleus going to be split by a carbon-12 nucleus? It's not, because a carbon-12 nucleus isn't NMR active. And so what's the likelihood of actually having a carbon-13 next to a carbon-13 in some given sample? It's basically 1% of 1%, right? It's very unlikely that we're going to see 2 carbon-13s next to each other. And because of that, we just don't see any splitting. So instead, what we end up seeing are these singlets down here. So we'll only see singlets when we're talking about carbon-13. What we could see is a little bit of decoupling from the protons, right? And so to basically overcome that, because that complicates things a lot. So to overcome that, we can essentially do an experiment that wipes out all of those splittings. And so that's what's commonly done. We just get rid of any of the splitting that would be done with a proton so that we can keep our nice pretty singlets down here. And so that's called proton decoupling. So, yeah, we've got all singlets. And so unlike proton NMR, where our typical shift was between 0 and 10 ppm, the frequency changes a little bit with carbons, and so now it's somewhere between 0 and really more like 200 ppm. So the same idea is still in play though. So when we have a carbon that's more de-shielded, we expect a more downfield shift. And so instead of a proton that shifted to maybe about 4, we end up seeing a carbon that shifted way down to like 100 or something. We just changed the scale. The same concepts are in play in terms of de-shielding. So when we look at a chemical shift table, let's see, a typical alkane proton we know is somewhere, this is listing it as 0.5 to 3. And so these tables are a little bit like pKa tables in that there's a lot of different molecules that can exist with their own unique chemical shifts that we see in an actual spectrum. And so what we end up seeing is this is actually listing 0.5 to 3. I think I gave you like 0.8 to 1.7 in the notes. The point is it's a range, right? We're going to have some range, and all the protons in that range we expect to be a certain kind of proton. All right, so alternatively, when we look up here and we see the same alkane, we can see that in a C NMR or in a carbon NMR, that shift is about 0 to 40. All right, so let's think about something else that we've talked about. So next up, we know that an alkyne is shifted down to about 2.5 to 3.1. So here we've got our alkyne and a proton. You can see that our alkyne and a carbon is about 65 to 85. So it is further downfield. Then we can look at, let's see, we can look at an alkene. And so we see that's further downfield, like a 5 to 6, and so we expect it to be further downfield for the carbon, and in fact it is. So just like we go from around 3 to about 5 here, we're going to go from about 70 upwards to like 100 to 150. And so just like with the protons where we're shifting further downfield, we're just doing the same exact thing with the carbon. The only difference is that our scale has changed. So here's our alkene, and then finally, we talked about benzene type structures, and so that's what the aromatic peaks are. We can see that for a proton, that's shifted down to 7 to 9. Aromatic peaks for a carbon are downfield like 110 to 160. So again, often you can't tell specifically based off of a chemical shift what you've got, and so that's why we have to use all sorts of pieces of information to ultimately arrive at the full picture of what we're doing. All right, I think that's going to have to be it on time. Let's see, 10:40. Yeah, we'll call it. We've got exams, so. So as a group, things really honestly went up on this exam. So the average, I think I said, was like a 145, which was up from a 139. Even further up was the median. And so the median jumped. On exam 1, the median was like a 140 or so. This time the median was a 151. So that came up quite a bit. The average being 6 points lower than the median indicates that there, in this case, were some scores that were lower and are kind of hurting the average. So I just wanted to, I say this a lot throughout the semester. I know I just said this in an email. But if you've got concerns about your grade, you need to get in touch with me. One thing that I emphasize a lot is that, by the end of the semester, if you show me that you have mastered this material, I don't really care how good you were at it in February, right? The point of this is I want you to learn organic chemistry. And so if by May 4th, when you take the final, if you have aced organic chemistry, I'll give you a grade that is indicative of you having aced organic chemistry. So as a whole, things have gone up, but there were some lower scores, and I want to make sure that we're all on the same page for that. The rough grade breakdown, the AB line around the 170, the BC line around the 140, the CD line around the 110. So basically 30-point gaps for the grades. We had more A's than C's on this one. I think we had like 95 A's. So nice job on A. Let's see. Oh, one more thing. So I had graders to help me out with the grading of this exam, and so what that means is the grading might not be perfect. If you have grading questions, please get in touch with me so we can get to the bottom of that. And then furthermore, I've listed your scores on Blackboard. Make sure that that matches the score on your exam. Help keep me accountable, making sure that I have the right numbers. All right, this is A to G. A to G over here. This is H to R. And then the rest of the alphabet.
Jump, yeah. Ooh, okay. 8, 10.
And if you don't want to wait around, I'll be in my office all day, so you can also stop by after.
Gotta be before this one. Ah. There we go.
Oh, and one more thing while you're still here. So 11 o'clock was a little higher on exam 1. You guys are a little higher on this exam. So by about half a point. That's I believe R is here, and then the rest of the alphabet is there. Yeah, I'll send out an email after class.
Okay, great. Yeah, I'd love to go over
2:30.
Yeah, great. Thank you.
Sorry. Very good.
Yeah, so when we look at our peaks, what we end up with are 2 doublets, right? So furthermore, we've got 2 protons here represented by this doublet, and then 2 protons by this doublet. So first off, because we've got 2 signals, we know we've got 2 equivalent pairs of protons, right? And so furthermore, if we look at the meta, we know it can't be this one, because here we have our own proton. Here and here we have 2 electrons. So we have 3 lines, so we know it's not meta. It could be ortho, but if it were ortho, these protons down here would be split basically by their neighbors, right, on both sides.
Right.
And so we would expect a triplet in that case, but that's not what we see. In this case, we see just the 2 doublets. And so what that is indicative of is we've certainly got a pair as a rotation.
Okay. Because you only have one thing, another single next to it, so then you get a duplet.
Yeah.
Okay, cool. Yeah, thank you.
If it was meta, you know, you don't always get the most distinct signals from benzene, so you could see 3 signals, but you could also have overlap that just looks like a jumbled mess. So while you can get some information from the benzene peaks, you don't always get the information that you look for.
Okay.
So,
If I want to take it with my section, is it possible to think about it?
that is possible. What?
Can I quickly ask, like, well, where these points were?
Yeah, so this is
Just wanted to know real quick. Thank you.